Okay, can you hear me? And can you... Oh, good. Okay. I don't know what I can do about it being blurry. But I'll try to write big. Okay, so anybody, first of all, you don't have to stick around if you don't have questions. If you've typed your name in, I've got you on the list, so you're good for bonus points. But since we're here, if anyone has any questions, now's a good time to ask. Any topics that are going to be on the midterm, or for those of you who've already taken the midterm, any topics from the later material that you'd like me to go over? Bye, Kelly. So everybody's good with, usually set theory is the one that people have the easiest time with, except for the survey questions with the complicated Venn diagrams. And then logic is a little bit more challenging. And then some of the geometry questions. So are any of those things that you had trouble with? Or just general questions? Any questions about testing? Finding the area of a semicircle and a rectangle. Yes, I think I know what you're talking about. Let me see. Okay, so For example, one of the questions from your ebook gives you a diagram that looks kind of like a football field. It's got a rectangle and then it's got a semicircle on each end. Tells you that these are right angles, which is how you know that this portion is a rectangle. And it also tells you specifically that these are semicircles. The dimensions are indicated only with a line which would be the center of the circle there, and 3 and 3. So what they're telling us is that this semicircle has a radius of 3. Okay, so if we have to find the area of the whole figure, we have to approach the problem by breaking it down into parts, right? So, are you with me so far, Joshua? Good. Okay, so what we're going to do is you can do it one of two ways. You can find the area of a semicircle by using the fact that the area of a circle is pi times the radius squared. And a semicircle is half the size of a whole circle. So the area of a semicircle is 1/2 pi r squared. So what that means is that we're going to add up one semicircle area over here on the left, and then another semicircle area over here on the right. And then of course we need to know the area of a rectangle is the length times the width. So we'll also add the area of the rectangle here in yellow. Okay, so we're going to have 1/2 pi times the radius squared for one semicircle, plus 1/2 pi times the radius squared for the area of the other semicircle, plus length times width for the rectangle. Okay, so we have 3 variables here that we need to find the values for. So what did we say was r? The radius. Good, it's going to be 3. So we're going to have 1/2 pi times 3 squared plus 1/2 pi times 3 squared plus, what would L, the length of, oh, and I forgot to give you L, that's going to be a problem. So also in the diagram they gave us an 8 here, which is our length, L. So we're going to have 8 times, what would the width of the rectangle be? Good, 6, that's right. 3 plus 3, so 6. So we're going to have 1/2 pi times 9 plus 1/2 pi times 9 plus 6 times 8 is 48. Now, one of the problems people have is plugging this into their calculator. In the instructions, they tell us to use 3.14 as an estimate for pi. This is important because your calculator actually has a pi button. And if you use the pi button, your calculator is going to take the approximation of pi out to many decimal places. And as a result, you might actually get a slightly different answer than the one they're looking for in the book. So just a word of warning, please make sure that when you're calculating this that you use 3.14 for pi. Okay. Another thing is if you try to type in 1/2 as a fraction on some calculators, that can cause some order of operations problems. So what I would probably do is go ahead and calculate as 0.5 your 1/2 times 3.14 times 9. Okay, now whatever you get for that, that's the area of one of the semicircles, and you're going to have the same value for the second one. So you're going to add that number to itself, or you could think of it as multiplying it by 2. So let me pull up a calculator. I don't know if you'll be able to see it because it's kind of small, but yeah, it doesn't get any bigger. Okay, so what we're going to do is 0.5 times 3.14 times 9, yeah, 3 squared is 9. So that's going to be 14.13. Notice I'm not rounding anything off. 14, you don't want to ever round off till the very last step and then only according to the instructions. So if we have 14.13 plus 14.13 plus 48. So 14.13, you can either type plus 14.13 or just multiply by 2 if you prefer. And then plus 48 equals, and we get a total of 76.26. Now in the instructions, they asked us to round to the nearest hundredth. So the 2 is in the tenths place, the 6 is in the hundredths place, so we're already to the nearest hundredth. In this case, they did not give us any dimensions, and so what I mean by that is, sorry, not dimensions, units. They didn't give us any units, so we don't know if this is centimeters or feet or whatever. But let's say we called this just 3 units and 3 units. These are linear units. So just to remind you, when you calculate areas, you're going to always have square units. So I would write 76.26 square units. Okay. So does that answer your question? Great. Okay, and I see T. Russell. You have a question on Venn diagrams. So Venn diagrams is a pretty big topic. Is there perhaps an example of a question, or if you could give me a little bit more description of what you want to look at? I'm not sure how basic to go. For example, are you okay with 2-set Venn diagrams but just having trouble with 3-set Venn diagrams? Are you talking about survey questions where it's a word problem and they say like 3 students study at the library and 5 students study at the library or the dormitory, that kind of question? So what I mean by a two-set Venn diagram is something, see, this big box is always the universal set, but within the universal set, which we call U, in our Venn diagram, we're going to have circles that represent the sets within U. So a typical two-set Venn diagram would look like this. Here's A, here's B, those are our sets. And there are all types of questions that we can ask about this. For example, I could tell you that the cardinality, or which is a word you need to know, it just means the number of elements in a set. I could tell you the cardinality of A, the number of elements in A is 10. I could tell you the number of elements in A union B is 12, and I could tell you that the number of elements in A intersect B is 1. And I could ask you to try to end that the number of elements that are not in A is not in, yeah, let's do not in A, is 5. And I could ask you to fill in the cardinalities of the different regions. So there's a difference between a set and a region. The circles are sets, but these two circles divide this whole universal set into several regions. So I'm going to label them with Roman numerals. Let's call this region outside of A and B Roman numeral 1. Inside of A but not in B would be Roman numeral 2. The intersection or overlap between A and B, that'll be our third region. And then this portion of B that's not in A would be Roman numeral 4. So could we get all of these regions? Could we figure out how many elements are in each one of these based on the information that we were given? It would be the question. So where students get confused here is, for example, when I say the number of elements in A is 10, a lot of times people think that means that there's 10 elements in this region 2 here, the part that's in A but not in B, but that's not what it's saying. A includes both region 2 and region 3. So it would be incorrect to just write 10 in one of those regions. It's split between the two. So be aware of that. What you want to do when you see a list of facts like this is you want to look for any of these that describes just a single region. So I'm going to go through here and like A union B. Oh, you can't see the thing. Hold on. No, you can. So A union B, it is actually talking about 3 different regions. Region 2, region 3, and region 4. So these 12 regions, but we don't know how. So we're not going to start with that information. Let's look at A intersect B. A intersect B is just the overlap between A and B here. So that's just one region, so that's good. It's region have exactly one element. So you would fill that in. You'd say, okay, there's one guy here. Can you see that, or is it too small on the screen? I know it's a little blurry. Okay, so so you fill in how many are in that region, and what I like to do is just to cross off the facts that I've already used. So I already used this fact, so I'm going to cross it off, and now I'm actually going to go back and notice that we were told how many elements were in all of set A, and there were 10 elements in all of set A, which includes only regions 2 and 3. Well, if we know that there's 1 in region 3 and 10 altogether, that means that region 2 must have 10 minus 1 equals 9 elements. So then we could figure out how many elements are in that part, the part here in pink. Okay, so now I've used that fact, so I'm going to cross that off my list. Now our goal here is to figure out how many elements are in each one of the regions. So we're going to move on to another fact and see if we can figure out how many's in region 4 that's just B but not A. So we were told that altogether in A union B, which remember includes 3 regions, 2, 3, and 4, that there were 12. And notice we now know 2 of those regions specifically. Region 2 had 9 and region 3 had 1. So that only leaves region 4. So that means that in region 4 that we must have 12 minus the 9 and the 1, or 10. So that means that there can only be 2 left over in region 4. So I'm going to put up here in region 4, which I'll go ahead and highlight that in green just to be clear. Okay, there are 2 in region 4. So I've used that fact. So I'm going to cross that off my list. Okay, now there's 1 region left, region 1. This is the part of the universal set that is outside of A and B that we still need to label. But what we were told is that the number of elements that are not in A is 5. Okay, so let's talk about what this A complement or not in A means. So A included regions 2 and 3. So everything that's not in A would be everything else. So it's not regions 2 or 3. So what does that mean? That means the region 1, it's outside of both A and B, or region 4. Hi Dakota, thank you for checking in. That'll be just fine. So 1 and 4 are exactly what we mean when we say not in A. So we're saying that between regions 1 and 4 there are 5 elements. It could be that there are 2 in region 1 and 3 in region 4. It could be, you know, there's 1 in region 1 and 4 in region 4. We don't know. So how can we figure that out? Well, looking back up here, notice that we figured out that region 4 actually has 2 elements in it. So in order to find how many must be in region 1, we're going to take the 5 we know are in both combined, subtract 2, and that leaves 3 that are out here in the outside part of the universal set. So we're done with that fact, and we have all of our regions. We figured out the cardinalities of each of our regions. Now, you can have a similar type of problem with a 3-set Venn diagram. So I don't know if anyone's interested in seeing that, or if you want to see something else. Yes, a 3-set Venn diagram. Okay. Okay, I'm looking up a 3-set Venn diagram question. Okay, so here's one. We have, this is actually number 2, section 2.4, number 15 or something close to that in the new edition of the book. 2.4.15 said the number of elements in a set A is 57. The number of elements in A intersect B is 35. The number of elements in A union B is equal to 81. The number of elements in A intersect B intersect C is 15. The number of elements in A intersect C is 21. The number of elements in B intersect C is 25. The number of elements in C is 49. The number of elements that are not in B is 52. And so whenever, and they're asking us to draw an appropriate Venn diagram and use the given information to fill in the number of elements in each region. So let's draw our diagram. It just means a big rectangle with 3 big circles. Draw it as big as you can on your paper so that you have room to work out the, fill in the number of elements in each region. Let's see here. Okay, so here's our universal set U. I'm going to put in some circles to represent my 3 sets. Okay, now we have to where there's a region where each of the sets overlaps each of the other sets, and there's a region where all 3 overlap as well. Okay, now it doesn't matter how you label them, but if you're following along on your paper, just to make it easier for us to talk about it, you probably want to label your sets the same way that I do. Here I have the 2 circles on top and 1 on the bottom. I'm going to label A on the left, B on the right, and C on the bottom. That doesn't really matter, but again, it'll make it easier for you to follow. So I'm also going to label each of the regions with a lowercase letter. This is only so that when I'm talking to you about it, that you know what region I'm talking about. So for example, here, this little almost triangular region in the very center where they all three overlap, we'll call that little a. And this region above it will be little b. To the left will be little c. Go talk. To the right will be little d. And then we'll have little e. Little f will be part of a. Little g will be part of c. And little h will be the part of the universal set that doesn't overlap any of the other sets. And I probably should label this U. Okay, so that's how you set it up. And now what you have to do is you have to go through and interpret which regions they're talking about. So for example, with the set A, we are talking about regions A, B, F, and C. Okay, so when they say there are 57 elements in A, that the cardinality, in other words, of A is 57, those 57 things are spread out within those four regions. We don't know how. A intersect B is talking about which two regions? Can you see which two regions are part of A intersect B? Remember, intersect means the overlapping portion, right? So where do we see an overlap between A and B, those two circles? Anybody? How about T. Russell? Do you have a guess which regions? Are you still there? What's going on? Joshua, you're still here. Did you want to see how the rest of this problem works out? Or was there something else you wanted to see? Because this is probably going to be the last problem that I can work, so I want to use our time in a beneficial way. Okay, so you don't need to see this one. So anything else? Okay, well, I think I'm going to log off then. So what you can always do, of course, is send me an Ask My Instructor question. Or if you prefer not to do that, you can always take a picture of a question and send it as an attachment in an email through Canvas or regular email. Okay. Thank you guys for coming. And by the way, I do know that my math lab's been down for maintenance, and that's caused some delay. So as soon as I can get back in, I'm going to be extending some deadlines. So email me if you have any questions about that. Okay. For some survey questions on the Venn diagrams. No, I don't know when the website is supposed to be back. I thought it was supposed to be back up already. But I'll be checking on it and try to keep you guys posted. Okay. All right. Well, keep working hard and don't be a stranger. If you have even a small question, just touch base with me, okay? Thanks, guys.